Hi everyone to another seminar at Physics Latam. Today we are kicking off the final mini course of this year, 2024. Over the past year, we have an incredible lineup of more than 60 speakers delivering both single seminars and mini courses on topics ranging from theoretical physics to pure mathematics. I'm pleased and proud of what we have accomplished this year, and I hope we can continue to grow up this project, bringing even more advanced topics and outstanding speakers in the future. To close up this year, we are happy to welcome Rachel Webb, who will give in a course on geometric invariant theory, stacks, and Quasimap's theory. Rachel is an assistant professor at Cornell University. She obtained her PhD in 2020 at the University of Michigan, studied algebra-geometric problems motivated by Chroma-Witten theory, especially questions about moduly of curves and stable maps. A major theme of her research is to understand physical linear sigma models. She is also interested in mathematical communication in all contexts and has many workshops and writings on this subject. Maybe she can tell us more on this later on. Please remember to raise your hand if you have any questions, and now I'll leave you with Rachel. Please go ahead.
Thank you for the introduction. So what I'm going to tell you about, I want to tell you about Quasimap theory, but I want to do it in a way that hopefully I will also tell you about some more general fundamental things that will be useful even if you're not interested in Quasimap theory. And so I'm going to start with an overview that introduces some of the concepts that I'll be speaking about in all of these lectures. So first of all, matter of housekeeping, in all of these lectures, I will be working over the complex numbers and even more specifically with things that are locally of finite type over the complex numbers. So let me start with some motivation for GIT, which stands for geometric invariant theory. This will be the main topic for today's lecture, but it will be a theme throughout. So the motivating question is, if G is a complex reductive group, if you don't know what that is, just think of G as a product of general linear groups. So if I have a product of general linear groups that acts linearly on an affine variety X, and if you don't know what a variety is, just think manifold. Or really, X will almost always be a vector space, C to the n. So whenever I have a group acting on a space, I can form the set of orbits. And I'll just write that X quotient G. And this set of orbits, if X was a topological space, then the set of orbits is naturally a topological space with the quotient topology. And the question is, when is that topological space naturally a complex variety? Or again, when is it naturally a manifold? And so here's an example. This is the projective space example. So G will be the group C cross, and I'll let it act on C to the n by the rule T acts on a point x1 up to xn equals tx1, txn. So I'm just scaling each coordinate. Let's draw a picture of what's going on. Here's a real cartoon when n equals 2. So I want to think about what is x mod g. This is a picture of x, and I want to think about what is x mod g, what is the set of orbits. So let's think about the orbits. if I pick the origin, and then I act by points of C cross, I stay at the origin, so there's an orbit. If I pick some other line, then the orbit will be the line through the origin, of course, not including the origin. And so X mod G, the set of orbits, is going to be, well, it kind of looks like projective space. So here I have this circle is the set of lines in real 2 space. But then there's this extra origin, and somehow each of these lines is close to that origin. More specifically, the closure of the line contains the origin. So here's my picture, X mapping down to X mod G. And the point is that this set of orbits has non-closed points. And depending on how much you know, well, it has no closed points, therefore is not a variety. Now, depending on how much you know, that sentence might be confusing. This green point is not closed. The sentence might be confusing because, of course, in the Zariski topology, we regularly work with points that are not closed. So if you do feel confused by this sentence as I wrote it, you can modify it to say that X mod G has non-closed C points. Therefore, it is not going to be the topological space of a variety. But I called this the projective space example, and that's because if I take X and I delete the origin, and then quotient by the same group action, then I've exactly removed this red point in the middle. So now this is just genuine lines through the origin. And so the quotient itself is projective space. Okay, so that's example number 1. Example number 2 is called the flop example. And this will be a really critical picture. So here, G will be the same group. But I'm going to change the action. So I'm going to, let's say on 2n, axon C to the 2n. And I have n x coordinates and n y coordinates. And I'll scale the x coordinates, but then I'll act by t inverse on the y coordinates. Okay, so let's do the same thing. Let's draw the picture of the orbits in this example. And again, let's draw the picture in 2 dimensions. So because of how I set things up, this will be when n equals 1. The thing to note is that, I'll write it down here, the orbits, so this now is going to be a picture of the xy plane, and the orbits will be sets satisfying xy is equal to a constant a. And again, I'll draw the real cartoon. So if x times y is non-zero, then in R2, this is just the graph of a hyperbola. So we get some different things like this. But when xy equals 0, we get 3 distinct orbits. So when xy equals 0, I could either have that x is 0 and y is not 0. Okay, so x equals 0, y is not 0. Or I could have that y is 0 and x is not 0. My orbits are not supposed to overlap, by the way. Or finally, I could have that x and y are both 0. Okay, so I guess I labeled the green orbit, yellow, red, you can figure out for yourself. So let's draw the picture of the quotient. So what does the quotient look like? Well, mostly it's parameterized by A. Most of the time, this is the A line. So the quotient x by g mostly looks like C with the parameter A. But when A equals 0, I actually have 3 points. So in other words, this is a line with 3 origins. Green is my other one. Oh, yellow. Okay, so these 2 blue orbits are somewhere over here. Hopefully this picture makes a little bit of sense. Most of the orbits are hyperbolas, but then when A equals 0, I get 3 orbits. Once again, in this picture, the yellow and green orbits are not closed. They contain the red orbit in their closure. And so these will correspond in x mod g to 2 points that are not closed. And that means that this quotient cannot be a variety. Like the space I've drawn there is not Hausdorff. But just like before we could delete the origin and get projective space, an actual variety, we can do similar here, but now we have to make a choice. So like this quotient, this x mod g quotient right here, it looks like it wants to be C, but I have a choice of 3 origins, so I need to just pick one of them. And so there's 2 ways to do that. And so I can either, at the risk of using too many colors, I can either use this copy of C right here and pick the green origin, or I can use this copy of C right here and pick the yellow origin. Those are my 2 choices. So in other words, I'm either saying that x is non-zero or that y is non-zero. So I delete where my x underline means like the vector x1 up to xn. So if I delete the locus where x is 0 and then do the quotient, what you end up getting, the quotient itself, is the total space of n copies of O of -1 on Pn minus 1. So you can ponder this. And likewise, if I delete the other side, in general, for general n, I get the same quotient, but the key point is that it arose in a different way. And so this business here, when n equals 1, like in the example, the quotients are both C. This Pn minus 1, when n is equal to 1, Pn minus 1 is a point, and this bundle is just a line. Okay. So the takeaways from these examples, in fact, if we have a vector space and a linear action of a reductive group or product of general linear groups, so linear action, this quotient, this topological space, is actually never a variety. Unless the action is trivial. And if the action is trivial, then the orbits are just the same as the points you started with, and so the quotient doesn't do anything. Basically, the origin is always going to cause problems. But you can often choose, and you have to make a choice, some closed subset of the vector space such that once you delete it, the quotient is a variety. And GIT is a package for doing this. So what is GIT? It is some tools that tell you how to delete closed subsets from representations so that the quotient is a variety or a Deligne-Mumford stack. We'll talk about those tomorrow. And so why should you care? First reason to care is that you can often compute things for these GIT quotients. So projective space was an example of a GIT quotient. You can compute a lot of things explicitly for projective space. A lot of things you can compute for projective space. You can also compute them for these GIT quotients. We'll see some examples of that today. A second reason is that these GIT quotients allow you to study birational transformations very explicitly. So the second example up here I called a flop. This is an example of a flop. The total spaces of these two bundles are related by a flop. And so this by viewing these as two GIT quotients of the same vector space, I get some very explicit coordinates on everything that's going on, and that can be really useful. You can also realize blowups as GIT quotients, and people definitely have made good use of that. Okay, and then a third reason, since this is a physics seminar, I feel like I should say some physics words. GIT is a baby example of a physical gauged linear sigma model. Or in other words, a GLSM, gauged linear sigma model. And I won't talk too much about that. But if you have some reason to care about GLSMs, then that is why you care about GIT. So my goal in these talks is to give you some snapshot of what 1 and 2 look like in math, of what it looks like to do computations with GIT quotients, and how to think about birational transformations arising from them. And so the structure of the lectures today is going to be GIT, and next time more or less will be stacks. So these first two are longer than the last two, and maybe they will overflow a bit. Maybe they'll take a little bit more than 2 days, I don't know. But then the last two are a little bit shorter in content. So on day 3, we're going to talk about something called walls. And these are going to arise in both GIT and in stable maps theory. So we'll actually kind of circle back to GIT on day 3 and talk about it in another way. And then on the last day, we'll talk more directly about applications. And we'll be talking about the Quasimap I function. Any questions?
Maybe it's also a good point to comment on the handouts.
Oh yes, thank you. I meant to mention that. So, right. So I always struggle when I'm giving a talk, like how rigorous I'm supposed to be. So this time I wrote down the proofs of a lot of statements that I'll be making in lectures, and I've called these handouts. And so they are available somewhere, I think, next to where you found the Zoom link for this talk, presumably. So hopefully those are useful. I'm going to be more conceptual in the lectures, but if you ever want to actually get your teeth into what I'm saying and figure out what's actually going on, then I refer you to those handouts. Okay. Oh, and my notes are reminding me, I did want to mention about these applications, kind of a selling point, I guess. So some things I want to do, I'll be giving a mathematical derivation of Morrison-Plusser's linear sigma model. Again, if there's any physicists for whom those are meaningful words. And the Quasimap I functions that we'll be talking about, these were series used by various people, by Giventhal, Lien, Liu, and Yao, to verify the predictions, the famous quintic predictions of Candelas, de la Osa, Green, and Parkes. So we'll see a mathematical derivation of some famous series that plays an important role in quintic mirror symmetry. Okay, so now we are going to move into some content, some definitions and examples of GIT. And I think I will, so I don't run out of PDF, try zooming in. So that I can write smaller relative to the screen. Okay. So as before, fix your complex reductive group, which I'm always just going to write on the screen as a product of general linear groups. But if you know about other matrix groups, for example, or like SO or SP or products of those with tori, you can insert those whenever I write product of general linear groups. And then X is a complex vector space. So just some very basic definitions to get us all on the same page. A linear action of G on X is one where the rule X maps to G acting on X is a linear map for every element of G. In other words, we have a group homomorphism from G to GLX. A character of a group is just a homomorphism to the torus. I'll usually denote it with theta. And then here's a big definition that I want you to mostly ignore, unless you have seen this before. The GIT semi-stable locus, and by ignore, I mean ignore the precise definition, but you should know that like there is a definition. There is a thing called a GIT semi-stable locus, and it will be, in fact, an open subset of X. Okay, and so the recipe really takes a while to parse. It's the set of points with the following property. For each group homomorphism, which I'll call lambda, from C cross to G, the following implication holds. Okay, so I'm going to write an implication. I'm going to put it in parentheses to try to emphasize. For every lambda, this implication needs to be true. The implication is that the limit lambda of t dot x exists implies that the composition of theta and lambda, this will always be a power of t. And the statement is that it has to be a non-negative, power of t. Close implication. So yeah, in other words, the semi-stable points are those with the property that for every one parameter subgroup, limit exists implies this pairing of the subgroup with theta is non-negative. That's one way you can say it. But once again, this exact definition we're not going to use in just a minute. I'm going to give you a much more concrete recipe for how to write down this semi-stable locus. So this is just on the screen for completeness. And again, for people maybe who've seen some of this before, then it might be useful to see again. Okay, so what is a GIT quotient? Well, actually, there's like lots of contexts for taking a GIT quotient. And so if you're ever talking to someone and they say, well, which GIT quotient? Or what do you mean exactly? And you want to refer to the one I'm telling you about, you can say, oh, it's the twisted affine GIT quotient. So and that is going to be the quotient of these semi-stable points, whatever they are. So maybe you haven't parsed the definition, but you know that given a theta, you get some choice of open subset of X, and the GIT quotient is just the quotient of those semi-stable points. And for now, we are just viewing this as a topological space, a set of orbits. It will inherit a topology from X. So earlier I did this example of projective space and a flop, and I had to take something out, and I referred to it as Z. So the Z, the thing I was taking out, is the complement of the semi-stable points. So you can either sort of focus on the things that you're removing or the things that are left. Okay. And so the upshot of all of these definitions is that given a vector space X, a reductive group G, and a character theta, sometimes I'll call this a GIT triple, there's this process called GIT, and what it gives you is a thing called the GIT quotient. That depends on all three pieces of the data. And for now, once again, we are viewing this as a topological space. So it gives us a new topological space. But next time, we will talk about the following perspective. So we will look at how G is acting on this set of semi-stable points. We'll look at its stabilizers. And we'll separate it into three cases. The stabilizers at all of the points might be trivial. In the projective space, in fact, in all the examples we did earlier, once I took out the origin or whatever bad stuff, the stabilizers of the remaining points were all trivial. But you could imagine they might be finite, like Z mod 3Z or something, or they could be infinite, like the stabilizer at the origin in those original examples was infinite. So we have these three cases, sort of an increasing badness, and then we will interpret this GIT quotient in one of the following three ways. So if all the stabilizers are trivial, then this quotient is a smooth variety, just like we got projective space earlier. If the stabilizers are finite, we will interpret this as a smooth Deligne-Mumford stack. I'll abbreviate it DM because I'm running out of space. And if the stabilizers are infinite, we'll interpret it as a smooth Artin stack. So just a little preview, we will be viewing these GIT quotients as stacks. For now, we're just viewing them as topological spaces. Okay, so I said you don't have to pay attention to this definition of the semi-stable locus because I will give you a more concrete formula for it in just a minute. And so here comes the more concrete formula. We are going to start with the abelian case. So suppose that our group is a torus of rank K, and this acts on a vector space by the rule, okay, so an arbitrary element of the torus is T1 to Tk acting on x1, xn equals, so it's a theorem that every torus action on a vector space can be written this way. You can choose a basis for the vector space and a basis, if you will, for the torus or isomorphism with C star to the K, so that the action does look like this. And so how does this action look? Again, it's kind of a lot of notation, but the point is that I am scaling each coordinate of the vector space by some monomial in the torus. So basically I'm saying there exists an eigenbasis, if you will, for this action. It's just scaling the coordinates. And then you can also, in general, write the character of a torus just as a monomial. So theta of T1 to Tk is Ti to the Bi. It's just a monomial in the Ti's. And so what's the point? The point is that all of this GIT data, in the case of a torus action, is encoded in some linear stuff. So the GIT data is all encoded in these AIJs and the BIs. So I'm going to write it in a matrix. The columns of the matrix correspond to the variables x1 up to xn. So the column n records the action on the variable xn. And the rows correspond, so this is columns correspond to x1 up to xn, rows correspond to the torus basis, T1 up to Tk. Then the other, we also have this B vector. So each of these columns I want to view as in both the matrix and the column vector. Columns are vectors in the character lattice tensored with R. That's exactly, they define a monomial in the torus, so that's exactly what you need to define a character. And then this guy right here, this matrix right here, this is called the weight matrix for the torus representation. And there's a general philosophy. I mean, I don't know, philosophy I feel like is too squishy of a word. I'm telling you, the only data going in here was the A's and B's. And so the philosophy is that all computational questions about the GIT quotient can be answered using or maybe in terms of, like, whatever the answer is, it will be stated in terms of the weight matrix and this B vector. this ends up being really powerful. So you can just write down a lot of information about a space if you have a presentation for it as a GIT quotient by a torus. And in particular, many toric varieties will arise as GIT quotients by tori. Okay, so an example of the philosophy is this formula that I have promised, the formula for the semi-stable points. So how do you write down the semi-stable points when G is I'm in the situation I just wrote down when G is a torus. It's a set of x's such that theta, I will have to tell you what this means. Theta is in the cone of the support of x. So what does that mean exactly? It means I can write theta as a sum. Okay, so cone means to take a non-negative rational combination of some vectors. So these CIs live in Q greater than or equal to 0. The AIs are exactly the columns of the weight matrix. And theta, I'm going to replace with this vector b. Theta is represented by b. And the support of x, by the support of x, I mean the coordinates of x that are non-zero. So the sum is over i's, indices I such that xi is non-zero. Okay, so when is x stable? It's stable if this b vector is in the cone generated by the coordinates of x, the cone over the a vectors corresponding to coordinates where x is non-zero. So it's still a little bit of a mental gymnastic, but it's something you can write down and practice pretty quickly once you get practice with the definition. So let's do some examples of this formula. Let's return to our projective space. So G is C cross, acts on x equals c to the n, and we're going to choose the character theta of t to equal t. So in this example, the weight matrix is, this t just scales every single coordinate, and so I write down the exponents, and it's just like 1, 1, 1, 1. And then the b thing is also 1. And so what are the semi-stable points? Well, I'm going to pick x's whose support will cone generate 1. And these columns, these ones, will cone generate 1 as long as I have at least one of them. In other words, as long as the support of x is not empty. And so this is exactly vectors who have at least one non-zero coordinate. So it's c to the n minus the origin. Again, I don't know if I said this. I use an underline to mean a vector of some kind. So here, this is the vector 0, 0, 0, 0. Okay. Let me just write down really quickly what you get for the flop. When theta of t is t, and we take the flop representation. Well, I can tell you exactly what the action is by writing down the weight matrix. So most of those the first n exponents were 1, and then the last n exponents were -1 in that representation. And then b is again 1 because I've chosen this character t. And so what are the semi-stable points? Well, this time, if I'm going to cone generate 1, if I only have negative ones, then I cannot cone generate 1. I cannot take positive linear combinations of -1 to get 1. So in order to cone generate 1, I'm going to need some of these 1s over here. In other words, to cone generate 1, the first n coordinates of x cannot all be 0. So I have c to the n without 0, but then the last n coordinates can be whatever they want. Okay, let's do a more exotic example. So now I have a rank 2 torus acting on C4, and I'm going to tell you the action with the weight matrix. So I have 2 coordinates of the torus, so there will be 2 rows. And so the torus, think of like, this is maybe s comma t. S comma t acts on the first coordinate by just multiplication by s, so I put a 1, 0. On the second coordinate, also multiplication by s. On the third coordinate, multiplication by t. And it acts on the fourth coordinate as multiplication by s to the minus n times t. So I write a minus n and a 1, just recording the exponents. And just so that I have a uniform picture, let's say that n is an integer, a positive integer. So there's a picture that goes with this information, and I will explain this picture a lot more in a couple of days when we come back to GIT. But I'm drawing here in the plane each of these column vectors. And I can pick a few different thetas now. So I can pick a theta over here, theta 1. I could pick a theta over here, theta 2. Maybe this is -1, comma 2. And I will leave it mostly as an exercise. I'll say a couple of words, I suppose. When you use theta 1, in order to cone generate theta 1, you are going to need at least one of these vectors. There's 2 of them. I drew like 2 arrows right there. I'm going to need at least one of these arrows, and I'm going to need at least one of these arrows. And what that translates to is that, let's see, the 2 arrows I've drawn in yellow were these coordinates. So they cannot both be 0 because I need something in my support living there. And the 2 vectors I drew in red correspond to the last 2 coordinates, so those also cannot simultaneously vanish. So you get this thing, and it turns out that the quotient is a projective bundle known as the Hertz-Brick surface. And if you do it for the other one, you'll find that you must always have this extreme vector over here on the edge. You always need that guy to cone generate theta 2. So that means that my 4th coordinate can never vanish. And then also the first 3 coordinates can't vanish simultaneously because I need at least one of those vectors to cone generate theta 2. And it turns out that the quotient is projective space again. So I have a 4-dimensional space and I'm quotienting by a 2-dimensional torus and I end up getting P2. Oh, in fact, a weighted P2. So if n equals 1, you get P2. So these are some different things you can get as GIT quotients, and I hope you are convinced at this point that at least when the group is a torus, you can just write down what it is. What about when the group is not a torus? So here's how you do it when the group is not a torus. Often in these lectures, we will understand things first for tori, and then we will bootstrap to non-abelian groups. And that process is often called abelianization. It might be better to call it non-abelianization, because like you understand the abelian case first, and then somehow you like non-abelianize your understanding. So if we have a complex reductive group or product of general linear groups, to take a special example, there will always be something called a maximal torus. So in this case of general linear groups, the maximal torus is just the product of subgroups of diagonal matrices. So I'll call diag of ki the subgroup of diagonal ki by ki matrices. And so if I have a G action on a vector space X, there's an induced T action, just restricting the action to this subgroup. And so I already know how to compute the semi-stable points for that T action. That was what I've been discussing for the last 10 minutes or so. And I can use that computation to write down the semi-stable points for this larger G action. But the way that it's easiest to write down is actually in terms of the unstable points. So the points that are not stable for the G action are precisely those that are in a G orbit of some point that is not stable for the T action. So let's see what this looks like in an example. Let's say G is the general linear group. Acts on K by N matrices. So this is a vector space, K times N dimensional vector space. And the action is that I left multiply. Left multiplication. And for a character, theta of G will be the determinant character. And let's also assume that K is strictly less than N. Okay, so to do this recipe, I'm supposed to look at the induced torus representation. So T in this example will just be diagonal matrices. Let's write a diagonal matrix T1 ... Tk, zeros elsewhere. And what are the weights? I need to write down a weight matrix to compute the semi-stable locus. So you have to think through, T is acting on a K by N matrix. You have to think through each coordinate of that matrix. How is that coordinate being scaled by this matrix? So when I multiply this diagonal matrix times a K by N matrix, it's going to scale everything on the top row by T1. So I'll have 1, 0, 0, 0 for everything being scaled by T1. So I'm going to have N copies of that. So this is the top row of my K by N matrix. Everything in that top row is scaled by T1. Everything in the second row is scaled by T2. And again, I have n copies. And so on until I get to the kth row, the bottom row, where everything is scaled by tk. So my weight matrix should have k times n columns because that's the dimension of X as a vector space. And then theta, if I turn it into a vector B, maybe I'll just write theta. Theta is as a vector. Well, what do I get when I take the determinant of this matrix? It's T1 times da 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 times Tk. And if I just write down the exponents are 1, 1, da da da, 1. So this is my B vector. It's just a vector of ones. And so to compute the semi-stable locus, I need to know when can I cone generate this vector of ones in terms of columns of this weight matrix, which are just standard basis vectors. And of course, I'm going to need one of each of those standard basis vectors. And in other words, I need, of T. I'm going to need some entry of each row to be non-zero. And so if we plug this into the formula, the unstable points for the G action will be the G orbit of the unstable points for the T action. Well, if I have k by n matrices and I throw away all of those which have, and I throw away those with the property that some entry in each row is non-zero, what is left is all matrices which have some row completely equal to 0. And if you take G here is GLK, so what happens when you take the GLK orbit of these matrices? I'm looking at all different row operations on matrices with a row of zeros. I'm going to get exactly matrices of low rank. Rank strictly less than k. Okay, so therefore, the semi-stable points are matrices of full rank. And so what is the GIT quotient? Well, I take full rank k by n matrices, and then I look at those modulo row operations, modulo elements of GLK. And so now that means when I do that quotient, I have a k-dimensional subspace of C to the n. So this is k-dimensional subspaces of C to the n, and that is exactly the Grassmannian, GRKN. So in other words, the Grassmannian is an example of a GIT quotient. So that was a very detailed example. For this last example, I'm not going to be detailed at all, but I want to tell you just a little about quiver varieties with possibly frozen vertices. So this is another big class of examples of non-abelian GIT quotients, and rather than tell you the definition abstractly, I'm just going to show you an example. So here is an example of a quiver. It's a directed graph, and there are integers on the vertices. This quiver has some frozen vertices, so the square is a frozen vertex. And such a picture encodes a representation of a product of general linear groups in the following way. So you take a general linear group for each unfrozen vertex. So for each circled vertex, oh, for fun, let me put an arrow like this. I can have arrows from a vertex to itself. And the space in question, I have a Hom space for each arrow in the picture. So if I call this arrow X, the corresponding Hom space is Homs from C2 to C2. Let's call these ones Y1 and Y2 and Z. So the Y's give me Homs from C2 to C5. And then I have, for our Z, I have Homs from C5 to C7. And let's call an element of this GL2 little g, and this GL, oops, that's supposed to be a 5. Because the 2 and the 5 are the circled vertices. Let's call that H. So now the action, you can, it's kind of what it has to be. Let's see, G belongs right there, H belongs right there. So G can act by conjugation on the map X. H and G together conjugate the Y maps. And H acts on Z. So you can imagine how this could generalize given any quiver, you get some representation of a product of general linear groups. And so there's a whole community that just studies, well, there's a whole community of people that study quiver representations. And so a lot is known about this specific type of example. And in particular, the semi-stable locus in this case can be described, oops, in terms of representations of the quiver, which is a different thing than the representation singular that I just showed you determined by the quiver. You can also talk about, well, it's related. This is the moduli of representations. So you can also talk about individual representations of this quiver, which are going to correspond to points in this X. And in terms of that representation theory, you can describe the semi-stable points. And if the GIT quotient is a variety, it is called a quiver variety. Or I call it a quiver variety. Okay. So very conveniently, we are at an hour, and this is also a very natural stopping point. So the remaining thing I will be telling you about today is some things that you can compute for GIT quotients. Okay, so now we are moving into, actually kind of lost track of how I numbered these sections. I think I started with 1. So some things you can compute. For X mod G. So this is going to be a very biased list just about things that I have experience using. There's definitely things you could add, but here's a couple that I have found useful. So first thing is that you can compute the Picard group. So there's a linearization map, which takes characters of your group. And so, oh, I should say, all of this is given a GIT triple. So I have X, which is C to the N, a vector space, G, general linear group, or more generally, a complex reductive group, product of such, and then theta is a character. So given an XG theta, there's a linearization map, which takes characters of G to the Picard group of this quotient. And so what does it do? Given a character rho, what is the associated line bundle? Well, we made X mod G, we made that GIT quotient as a quotient. So here I am writing down the GIT quotient as a quotient. We are going to make the line bundle also as a quotient. And the space we quotient is the semi-stable points cross C. So even before, maybe I should do it like this. Before I take a quotient, this is a vector bundle, a line bundle even, the trivial line bundle. But now G acts on both of these spaces, so it acts downstairs by whatever my original action was, and it acts upstairs by the diagonal action. So the action on X comma Z, this being a point in X cross C, is the action whatever I have on X, and it acts via the character rho on Z. So Z just gets scaled by rho of G. So that gives me an action upstairs as well. And if I quotient the whole thing, this is the line bundle L rho. So that is how a character defines a line bundle on a quotient. And, oh, I should maybe not use the square brackets. Square bracket means stack quotient, so we'll talk about that tomorrow. Today we are just thinking about topological spaces, or but yeah, this is actually a very general construction. And let me actually specialize further this whole chapter 3, specialize to the situation when this quotient is a variety. So referring back to the trichotomy I hinted at earlier, this is equivalent to asking for G to act with trivial stabilizers on the semi-stable locus. A lot of what is in chapter 3 is true in much more generality in a stack context as well, but let me just uniformly make that assumption so I don't have to worry about it. Okay, so at least with that assumption that the quotient is a variety, this map, no, actually I think I don't need that assumption here. This linearization map is always surjective. Every line bundle on a GIT quotient comes from a character. It is an isomorphism if the complement of the semi-stable points has codimension at least 2. So if the unstable locus has codimension at least 2, then this linearization map is an isomorphism, and the Picard group of the GIT quotient is exactly the group of characters of the group you used to make the quotient. So here come our examples. We should always test out everything for projective space. So what is the line bundle corresponding to the character? I'm going to write out the whole character. The character is theta of t equals t to the a. I should call it rho. Rho theta was for a different kind of character. Rho of t is t to the a. Okay, so what is this line bundle on projective space? Well, what you do is you write projective space as a quotient, so that's c to the n without 0. You form a trivial bundle, and you quotient that whole thing by a diagonal action, where the action on the first coordinates is however you make your GIT quotient, and on the last coordinate, it's by the character rho, defining the line bundle. Okay, so then the question is just, what is this? I claim that this is the total space of the bundle O of A on Pn minus 1. And how do you see that? How do you see that this is O of A? Hopefully it's O of A because I used the A character to make it. You can actually check that you get O of A. So you can determine this integer here by computing a transition function. So what that looks like is we write down a point in the vector bundle in the affine chart, say where x1 is not 0, or maybe we set it equal to 1. So here's a point in the bundle where x1 is equal to 1. And then using the action on this whole space, the C star action on the whole space, this point is equivalent to what I get when I act by x2 inverse. And I act x2 inverse because of a point in the affine chart where x2 is 1. And when I act by x2 inverse, this is going to be a mess. Let me just write it somewhere else so you can actually read it. Equivalent to x2 inverse 1, x2 inverse xn. When I act by x2 inverse, of course, this last one is x2 to the minus az. And so this is the transition function. When I went from x1 equals 1 to x2 equals 1, the fiber coordinate got multiplied by x2 minus a. And if you're me, then you just always have to look up in some exposition of bundles on P1 to find out if that means I got O of A or O of minus A. And it means that I got O of A. This is the transition function from the chart x1 equals 1 or not equal to 0 to x2 not equal to 0. So you can just see very explicitly what you get. So that's fun. And then, of course, I can also use this fact to say that these are all the line bundles on projective space. Because, I guess I should say that, because what is the unstable locus here? The unstable locus is the origin in Cn. So if n is at least 2, that unstable locus has codimension at least 2. And so the Picard group is exactly the characters of the group I used to make the GIT quotient, and the characters of C star are exactly the integers when the unstable locus has codimension at least 2, which is all of the cases you care about. Maybe it's worth thinking about what happens when n equals 1. Then x is C. The codimension of the unstable locus is then 1. The Picard group of p to the n minus 1, or p to the 0, will be the Picard group of a point, and of course all line bundles on a point are trivial. So this group is just 1. And so I have a surjection from the characters of C cross to the Picard group of this quotient, but it is clearly not an isomorphism. We can also compute the Picard group of the Grassmannian. So here, if I take the character, so remember, to make the Grassmannian, G was GLK, X was K by N matrices. So a character of GLK would be the determinant character, or some power of it. And this gives us the determinant of the universal subbundle on the Grassmannian, which again you could prove by computing transition functions. And this is the line bundle coming from the Plücker embedding of the Grassmannian. And just like for projective space, well, what is the unstable locus? For the Grassmannian, it was these matrices of low rank. And if you even think back to, like, just in the torus case, certainly matrices of low rank include matrices with a 0 row. And this k less than n condition ensures that that locus will have codimension at least 2. So the G orbit has the same dimension as those original T unstable points. So the Picard group of the Grassmannian is just the character group of GLK, and that is again Z. All characters of GLK are powers of the determinant character. Let me do one more example. This one hints at some other cool structure you can see that you can just read off of GIT quotients that I'm not going to talk about, but I don't know, I'll do this example and sort of hint at it. So this is the Hertzebruck example that we had earlier. So here's my weight matrix. And as an integer. So we had theta 1 and theta 2 earlier. Theta 1 was the character 1, 1. And unstable points that are not stable for that guy, were those for which either the first 2 coordinates were 0, so asterisk here means it could be anything, or the last 2 coordinates were 0, and the first 2 coordinates could be anything. And I want to point out that every component here has codimension 2. Because I have 2 zeros, that means I have codimension 2. And so in particular, this implies that the Picard group of the Hertzebruck surface is canonically isomorphic to characters of C star squared, which are going to be Z squared. But remember, we also had a weighted projective quotient. So for theta 2, a point was unstable if either the first 3 coordinates were all 0, or the last coordinate 0, and the first 3 could be anything. So here, this component of the unstable locus has codimension 1. And indeed, the quotient, or in this case, was a weighted projective space. Maybe let's take n equals 1, so we don't have to worry about weighted projective spaces. The quotient then is just P2. And we know the Picard group of P2. In fact, if you didn't know the Picard group of P2, I computed it for you 5 minutes ago. It was Z, in particular, not Z squared. And so here we have that, again, the characters surject onto the Picard group, but they're isomorphic. And this is not, there's a lot of structure going on here, so you can actually read off from this picture I drew earlier. Where did it go? This one. Based on this picture, you can actually just read off. It's important that some of these arrows, there's 2 of them, but you can read off for which of these thetas you will end up having an isomorphism of Picard groups with the torus, and for which the Picard group will actually be getting smaller. It's related to something called the movable cone. Okay, so that's the first thing. You can compute Picard groups. Second thing, you can, in fact, so you can work with line bundles. That's another way to say my first thing. You can work with line bundles on these GIT quotients. In fact, you can work with vector bundles. You can probably guess. So I already have my xg theta, but suppose I also have another vector space of dimension m, call it V, with another linear g action. So I already have my xg theta, and now I have an additional V. Such a thing, a representation, defines a vector bundle, and it's exactly the same way. So I have right here a trivial vector bundle on the semi-stable points before I quotient, and then I quotient everything by E, where g acts on x comma little v equals g acts on x, g acts on little v, just by the diagonal action. And so this will be the total space of a vector bundle on the GIT quotient. Let me call it E sub v, the vector bundle corresponding to v. So one cool thing you can do with this is you can actually describe the tangent bundle. Maybe I should say not all vector bundles quotient will arise this way. So before I had a linearization map for line bundles, it was surjective. I don't have a surjection like that for vector bundles. But for example, for the tangent bundle, I can explicitly resolve it. The tangent bundle. Okay, so for example, tangent bundle will usually not arise as a vector bundle associated to a representation. But I have an explicit presentation of the tangent bundle as a quotient of vector bundles arising from representations. So this is called the generalized Euler sequence. So given my xg theta, I can write tx mod theta by g as a quotient of the vector bundle on x mod theta g associated to x. So this is a tautological thing. I'm using x again, the same x, and for my v above to make a vector bundle. And I quotient that by a subbundle, which is determined by the representation, which is the tangent space, or Lie algebra of G. So this is a short exact sequence. So for example, you get the usual Euler sequence on projective space. So the vector bundle corresponding to X, this thing with like weights 1, 1, 1. If you scroll up to when I talked about the linearization map for Pn, you'll see this is n copies. So my weight matrix, maybe I should write down the weight matrix I'm using for this example, just to be clear. 1, 1, 1. These are all ones. There's n of them. Okay. And then the Lie algebra as a representation. Okay, so it's one-dimensional, and then as a representation, since the group is abelian, it's the trivial representation, and so that is the trivial bundle. So we get the usual Euler sequence on projective space. Any questions about line and vector bundles? Okay, the last thing I'm going to tell you about is Chow rings. And I can tell you for sure that this will be isomorphic to the cohomology ring when the quotient is projective. I suspect it is even without that assumption, but this was the reference I could find. So this is another situation where we're going to start with the abelian case and then do some non-abelianization. So you can just write down a formula for the Chow ring of this thing, which if you don't know about Chow, then just think about cohomology and you are certainly correct when the quotient is projective, which is going to be all of the examples I write down in this section. So my little subscript q on the outside means I'm tensoring with rationals. So what is the Chow ring? Well, I'm going to give you a presentation as a quotient of a polynomial ring, and the generators of the polynomial ring, I'm using H for hyperplane because of a projective space example that is in the future. But these H's are the Chern classes. Like, how are you going to get Chow or cohomology classes on your GIT quotient? Well, I've already told you how to get line bundles. And if you have line bundles, you can take characteristic classes. And so that gives you some natural classes on the quotient. And in particular, when we work with these torus representations, we like to choose bases for x and t, and we have a weight matrix. And because we chose a basis for t, we have a basis of projection characters. So I have these characters which send t1 ... tk to the ith coordinate. So h1 here is the first Chern class of the line bundle corresponding to the character that sends t1 ... tk to t1. So I have one of those projection characters for each index. Their Chern classes are these h's, and then I have to tell you the relations. The relations come from the choice of theta. So it is another initially hard to parse formula that becomes, it's very easy to apply once you have done it a few times. So I'll copy down the formula and then I'll tell you just where it comes from, how you should think about it geometrically. But you can see this is just something you can write down. It has our weight matrix entries in it, our AIJ. We can just write this down. So I have one relation for every index set, capital I, so here's my capital I, whose complement does not cone generate theta. It's related to semi-stability. So cap I, so these relations range over, so one relation for each capital I subset 1n such that the complement doesn't cone generate theta. And so what are these subsets? These actually index components of the unstable locus, if you just unwind all the definitions. So these some index set for components of unstable locus. And then what is the corresponding relation? This is actually the Euler class of the normal bundle to that component. Okay, so let's look at our projective space example. So I have an H for every projection character of the group. Remember, the representation here is just C star acting on Cn. So there's only one H. And then I have a relation for every subset 1 up to n whose complement doesn't cone generate. So there's only one subset of I1 up to n whose complement doesn't cone generate the 1. And that's the whole subset. So I just have I equals 1 up to n, giving me a relation. Its complement will be the empty set. So that certainly doesn't cone generate theta. So then I have a relation, which is for everything in I should take the entry of the weight matrix, like times the corresponding H. So just everything in I contributes an H, and I get H to the n, which is the usual. Like we know that's the answer. But you can use this formula to just write down Chow rings of more complex spaces. I've been debating whether or not to include the Hertzsprung example. I have time, so I guess I may as well. So if you go back and look up what was the weight matrix for this Hertzsprung surface, so I'm using a specific choice of theta, remember, to get this quotient. And what theta is it? I'll draw the picture again for you. This choice of theta lived right here. And so when I form my ring, this was a quotient by a rank 2 torus. So I'll have two classes. I'll call them F and C. F will be the class of a fiber, if you know already about the cohomology of a Hertzsprung surface. F is the fiber class, C is the curve class. And what relations do you get? Well, I'm supposed to get a relation for each cone that does not cone generate, for each subset of characters that doesn't cone generate my theta. And so what are those? There's, maybe I'll call it I1, has two things in it, which is these two vectors. So those certainly don't cone generate theta 1. Maybe I2 is these two vectors. So those also don't cone generate theta 1. So what does I1 give us? It gives us the relation for everything in here. So in other words, for these characters, these 1, 0s, I should have said F is the first, corresponds to C1 of the first projection. L, T, S maps to T. And this is C1 of L, T, comma, S maps to S. Anyway, so you can work this out. This I1 gives you F squared, and I2 gives you minus NF plus C times C. Anyway, so you can recover anything you want to about intersection theory of a Hertz-Brick surface from this formula. Okay, the example I wanted to finish off with, though, was the Grassmannian. So I give you a formula for the Chow ring of an abelian GIT quotient, but what about non-abelian ones? There's a general statement. You can find a reference in this handout. Right now, I'm just going to state it for the Grassmannian. And you should know, or I'll kind of say, that this can be generalized, except for like one thing, and all generalizes. So we'll be looking at the example where G is GLK. Maybe for just a minute, X is secretly going to be K by N matrices, but that won't even be important for just a minute. So I don't know, you can kind of cover that up for a minute. But then here's the data we're going to need to use. So we're going to have W is the while group. In general, this is the quotient of the normalizer of the maximal torus by the maximal torus, but in this example, it'll just be the symmetric group on K letters, SK. And then we have something called a fundamental anti-invariant. And maybe, I guess I'll write down, it's a product over positive roots. So this is some representation theory definition, but I'll tell you what it is in our example. The idea is that we are going to, oh, I'm copying my old notes. That's why I'm like, this is not, let me get the correct page of notes. Okay. So the idea is that we are going to describe the Chow ring of this quotient using the Chow ring of the quotient by the maximal torus. So let's figure out what that guy is in our Grassmannian example. Okay, the maximal torus, remember for the Grassmannian example, is the diagonal K by K matrices. And so if you let that act on K by N matrices, what we're actually going to get is K projective space representations, one for each row of the matrix, and each of those of length N. So what we actually get, we get a Pn minus 1 for each row of that K by N matrix. There's going to be K of them. And so we can write down the Chow group using the previous formula, or just using the fact that you know what the Chow or cohomology of projective space is. But we're going to have a generator for each torus factor. The torus has rank K, so I have H1 up to HK. And the relations, I have one relation for each projective space. So H1 to the N, HK to the N. Now I can tell you what delta is, and I should have done that in the other order, but now I can tell you what delta is. Delta is going to be a specific element of this Chow ring of the torus. So I can just write it down as a polynomial in H's, and it is the Vandermonde determinant. Product over I less than j, hi minus hj. So I can just tell you explicitly it has some abstract definition as well. Okay, so these are all of our ingredients, and now I can tell you what the Chow ring is. So what we do is there is a commuting diagram. You take the Chow ring of your abelian quotient, in this case, the Chow ring of a product of projective spaces. And the while group will act on that. In this case, the while group is Sk. How does Sk act on polynomials in k variables? Just by permuting the variables. So Sk permutes these h1 up to hk. And I take the invariant polynomials in the quotient ring. So these are symmetric polynomials. But I'm not allowing arbitrary, I'm quotienting by this ideal. On the other hand, I can take a symmetric polynomial and multiply it by the Vandermonde. So this down map is times delta times the Vandermonde determinant. And you may have seen this in some context before. If you take a symmetric polynomial and multiply it by the Vandermonde, what you get is an antisymmetric polynomial. In other words, if you let something in the symmetric group act on the Vandermonde itself, it will scale the Vandermonde by the sign of the permutation. So I'm going to use superscript A for anti-invariant. These are the anti-invariant elements of this quotient. So multiplication by the Vandermonde exactly takes symmetric or invariant polynomials to anti-invariant ones. And this down map is not an isomorphism with the domains that I've given it. But there are natural maps from either of these modules to the ring of the Grassmannian. And I could tell you what those are using the geometry of the situation. Maybe I won't, but you can say what they are. This one is a group isomorphism. And this one is a ring surjection. So this is a case where you can't have your cake and eat it too. You can either have a really good handle on the ring structure of the Chow ring of the Grassmannian, or you can have a really good handle on the modules. Like you can know what it is up to isomorphism, but then you don't know how to multiply things. And that's that is my very naive take on why Schubert calculus is a thing. It's trying to have your cake and eat it too. So this surjection right here is saying that classes on the Grassmannian can all be written as symmetric polynomials in Chern classes, in Chern roots of tautological. Everything can be written as a symmetric polynomial in the Chern roots of the tautological bundle. So these H's are the Chern roots of the tautological bundle on the Grassmannian. And the fact that this is a surjection says every class in the Grassmannian is a symmetric polynomial in those Chern roots. So let's just do a little bit more. I want to tie this into some Schubert calculus for those who have seen it, and give you a sneak peek of such if you haven't. So there's a natural basis for the bottom left corner in my triangle. What is the basis? You start with a monomial and you anti-symmetrize it. So start with a monomial having distinct exponents. We can even assume those exponents are decreasing. So here's a monomial in the h's. And let's assume the exponents are decreasing. By anti-symmetrize it, I mean, take this monomial, I act by an element of the symmetric group, and I add on what I get times the sign of the permutation. So if I just am transposing, I will add to this monomial -1 times its image under all transpositions. And so I get some polynomial where the coefficients of the terms are either plus or minus 1. And these things will be a basis for anti-symmetric polynomials. And this basis, elements of the basis are in bijection with these decreasing sequences of A, and because of the quotient condition, the most any of those could be is n minus 1. And so this elements of the basis are in bijection with strict staircases fitting in a k by n minus 1 box. So if I take my exponents a1 up to ak, the biggest one has to be at most n minus 1. So like, imagine this is all gridded out, and maybe it goes up to here, and then the next one has to be strictly smaller, and the next one has to be strictly smaller, maybe after a while it's a lot smaller, but strictly smaller. So this is my staircase fitting in a k by n minus 1 box. It's a strict staircase, meaning each row is shorter than the last. And you might recognize that this combinatorial gadget, this is encoding the basis of bialternates. Bialternates, which people write as the set of A sub lambda plus deltas. Delta here, so this is a picture of a lambda plus a delta. Delta is the partition k minus 1, k minus 2, and lambda is just whatever you get when you subtract delta. So when you the delta is the thing that makes it strict. And once you subtract that, this basis of bialternates, so this is the part that's special to a Grassmannian, is it can lift this basis of bialternates in a natural way to symmetric things. In general, I mean, there's always a choice, but there's sort of one natural way to do it for the Grassmannian. And that's the Schur functions. So these are called lambda. The delta is missing. And so the lambda now is a non-strict staircase that fits in a k by n minus k box. So you trim off this delta bit, and now the staircase doesn't have to be strict. You could have something, I'm sorry I didn't prepare a specific example, but you could have some stuff where your stairs are all the same height for a while. And so you get lambdas like that. And the relationship, it comes exactly from this Vandermonde determinant. The relationship is that delta times the Schur function is the A lambda plus delta. So if you've seen Schur functions before or bialternates before, my message here is that at some level, it makes sense to think about those objects for more general, or to think about those basic. At some level, that story generalizes to non-abelian GIT quotients. And that is the end of my talk for today.